You good? Okay. All right, everybody ready? Let's go. Here are a couple of acid-base reactions, like the ones we've gone through in class, and that I'm sure you encountered in the homework many times. So we're going to look at, these are acid-base reactions, so we're looking for the transfer of a hydrogen. Where does the hydrogen, the hydrogen ion, H+, where does it come from? Where does it go to? In this case, if you got to fill in the blanks like this, you want to look for the pairs. So you see that HSO4 is going to become SO4 by losing the H, right? So those would be a conjugate pair. This would be the acid. This would be the base. So conjugate acid, conjugate base. So that means that water is going to have some other thing here. Water is acting as an acid on this side with this base and a base over here. Someone's phone whistling? No. Okay. So we have to look at what's the conjugate base of water. That is water minus an H+, which is hydroxide. All right. Same idea for the second one. NH3 we know is a base, and HClO3 that's actually chloric acid, but doesn't matter what kind of acid it is. It's just an acid. It's got this H, which means the H is going to transfer to the ammonia. So you've got base, you've got acid. It's always a good bet to pick an acid if you see that H out in front. So H and stuff is generally the acid. So we want to look at what happens when the hydrogen goes from here over to here. Yep, that's going to give us ammonium, NH4+, okay? And then chlorate, which is ClO3-. So this will be paired up here, and this one over here. All right, pH, couple pH problems. Calculating the pH and then determining if it's acidic, basic, or neutral. So the pH we know is the negative log of the hydronium ion concentration. So you take the negative log of, in this case, 1.2 times 10 to the minus 8. So negative log is going to be, I think it comes out to 7.9. So the pH is 7.9. The best way to, there are two correct answers here. I would call this neutral. Between 6 and 8 is the neutral range. But of course, 7 is perfectly neutral. So above 7 is also basic. So I would also say basic is correct here. I think neutral is a better answer because a solution that's 7.9 would be neutral. It's like tap water, basically. Yeah, but I mean, nothing. So how above? Is 7.000001? Is that basic also? So that's pretty arbitrary. Again, these are just ranges. So the point of saying, the point of these three categories is to give us a sense of how this thing would behave. And so yes, you're correct. Above 7 would be basic. But in real practice, if we encountered a solution for pH 7.9, we would think of that solution as more neutral than basic. But so if somebody likes base, it's fine. No, it's right. Yeah. We'll put that in parentheses here. Yeah. So technically, you could call that basic. I think a better answer is to call that neutral. I will accept either. All right. So this time we're given the hydroxide ion concentration. This makes it a lot trickier because we can't just take the negative log of that. What do we have to do? Yeah, we have to get the hydronium. So there's two ways to do this. We can either get the hydronium ion first by dividing 10 to the minus 14 by the hydroxide ion concentration. Or, which is what, like 10 to the minus 2, something like that? Or we can take the negative log of the hydroxide ion concentration and then subtract it from 14. Either way, it gets the same answer. So I like that way just because then it's less dealing with big numbers with scientific notation. So I would say, all right, the POH is the negative log of 3.5 times 10 to the minus 12. And what is that? Do we have that handy? Let's see. about 11.4. And so then the pH is going to be 14 minus that, which is 2.6. So if you did it the other way, you would have gotten something times 10 to the minus 2. You take the negative log of that, you also get 2.6. All right, close enough. That's just a rounding error. Yeah. So this is what? Acidic, basic, or neutral? Yeah, this is acidic. Okay, good. And then finally, the conjugate base. Now, sometimes this is a little bit confusing to think about these things in these terms. Conjugate base is when something acts as an acid, loses its hydrogen, and then becomes a conjugate base. So some people like to actually set up a reaction where you see this happening. I think about it as what would happen if NH3 is an acid. It's going to lose hydrogen, and then what's left if it's lost H+? NH2 minus, right? Because the H+. So the conjugate base of NH3 is NH2 minus. It's NH2 after it loses its hydrogen ion. All right. Okay, so that was quiz 7, not 6. Okay. So I hope that went well. We'll probably have 2 more. So we'll do a quiz on Monday, because otherwise we'll have to wait till after the exam, and that won't make any sense. What?
Wasn't this a quiz?
This was a quiz. So we'll take another one on Monday. We would do it Wednesday, but there's no class Wednesday. So we'll have to do it Monday, and that'll be on the nuclear chemistry, the nuclear reactions and half-lives. So work on that this weekend and be ready for that. Then we'll have one more quiz after the exam, the week after, not the week of the exam, the week after the exam, which is the last week of classes on the organic chemistry stuff that we'll start today.
Does the pre-labs not count?
They do.
Oh, so those points are already calculated somewhere?
No, they're not posted. I just noticed they're not posted in Blackboard. I've got about half of them in now. I just did it this afternoon, so check again. The pre-lab, I think, is 5% of the grade overall, which is another good point. So another good reminder, the withdrawal deadline is Sunday. If anybody needs to get out of the class without a grade reported, Sunday is the time. I believe Sunday is the last chance you have to do that. If you're still in the class after Sunday, you will have a grade reported at the end, regardless of what it is. So hopefully it's a good one, but you know, most of your stuff is up there now. Yes, we're missing a couple labs and quizzes, but that shouldn't affect things too much. So what you see on Blackboard should be a reasonable approximation. That said, one thing that could really mess it up, the way I have it calculated on Blackboard right now, it drops your lowest exam. So the score on Blackboard is not counting your worst exam, which means that if your third exam is more like your good exam, whatever one was good, great, that's a good approximation. But if your third exam is more like your not as good exam, then your grade is going to drop considerably. So the grade that you have there, the weighted average at the end of the Blackboard thing, does not really take everything into account because it drops those lowest scores. And when there's another exam, then it's going to be based on 2 exams instead of just 1. So you see what I'm saying? So like if you had let's say you got an 80% on the first exam and then a 50 on the second exam. So that score is not including your 50, so your grade probably looks pretty good. And if that 50 were just kind of a fluke because you had a bad day and it was, the exam was a bad exam, then great, no problem. Come back and get an 80 on the third exam and everything's good. But then if that third exam is more like that 50, suddenly your grade's going to be a lot lower than what it looks like right now. All right, so.
Well, you drop the lowest.
I don't drop it exactly. I replace it with the score from the final, but for the final grade. But since we don't have a final right now, it's just the lowest grade is just dropped.
Okay, so that it's dropped and replaced with the final score?
Right.
Okay.
The final
so
exam
say
score.
you bomb the final, but on your say like your not so great test, you're still gonna wipe out that test even if it's a higher score than
No,
a final?
no. Only if it would help you to replace the score with the final,
Okay.
then I would replace it. But the final will still count regardless because it's the final.
What would you say if a student, what like percentile
If a
would you
student-
say for a student? If you see potential, like, okay, if you get a 70 or higher on your exam, on your final, and on your next test, I would not recommend you dropping the class, or do you have like a pre-notion, like you might, and it's probably in your best interest if you would just drop the class? Percentile, like if you are looking at grade, or like.
Right, like what it looks like right now,
Yeah,
I think it's really hard to say because I think it's an individual thing. You know, if somebody had a bad exam or even two bad exams because
yeah, like myself, I don't care.
okay, so because of stuff that happened, you know, you were sick or just didn't get on top of things for that exam or whatever, then you know that you're doing okay. The exams just aren't reflecting that, and there's a better chance that the next exams are going to go better. But remember that the class is largely cumulative, and so if you feel like you haven't really mastered that earlier stuff, then there's nothing to make me think that the next exams are really going to go any better. And so that's probably where you're at. I would say in general, assuming you've been doing the labs and everything, which most people have, the labs and the pre-labs and all of that tend to bring your grade up by about 5 to 10% over your exam average. So whatever your exam average is overall in the class, when you add in all that other stuff, which is usually what? Yeah. It's there, but it's not in the calculation. It's like I set up this final cut for the weighted average. I tell it what to count for that. So when I tell it to do that, I count only one exam. And it's also an individual decision about how bad it would be if you didn't get the grade you want if you stay in the class. You know, like how much of a risk is that for you? For some people, it doesn't really make much difference. For some people, they cannot have a low grade or whatever grade on their transcript, and it needs to not be there. So those people I would advise, if they're not, you know, if there's a chance of failing and you really can't have a failing grade on your transcript, then you probably want to think about withdrawing, I guess is how I would say it. But if you want to talk about further individually, talk to me, come talk to me, or send me an email or something, we can talk about it. Okay. All right, let's move on. So we're going to go on to the last part of the class, pretty much the last chapter, all right?
I'm not.
No?
I'm following like class by class.
Okay. He just sort of like fell over.
Oh no, I was getting back.
Okay.
What is this chapter?
Organic chemistry. So in the old books, I don't know about the really old book, but certainly that one. It's actually two chapters. Is that good? Good. Yeah, they don't actually change anything. They just repackage it so they can sell you
Make
a
it
new
more
one.
expensive.
So in that book, I believe it's chapters 10 and 11. In the new book, it's all condensed into one chapter. I think it's chapter, I should know that, chapter 11. Yeah, chapter 11 in the new book. In the old book, it's either 10 and 11 or 11 and 12. It's two chapters. Is that, yeah, 10 and 11. Right, this is where we would start. So Most people really like these chapters. We get away from from more of the math and the calculating things, and it's more about drawing pictures and writing chemical formulas and that part. So if you like that part, when we did that with reactions, it's going to be more similar to that. What is organic chemistry? What do you mean by that?
Something to do with hydrogen, right? Or carbon.
Something to do with hydrogen or carbon? Yeah.
There's some guy,
Anything else?
some patient's family just talked to me about it for like 30 minutes.
Oh yeah?
Yeah.
Sounds like an exciting day.
It's all based around like one molecule, right?
Yeah. Now the word organic has to do with coming from life or coming from organisms. In early days of chemistry, it was thought that there were two categories of compounds. You had your minerals and you had your organism things. So things that came from rocks and things that came from living things. And that was it. So you had like two classes of chemicals. Now, of course, we know it's a lot more complicated than that, and those categories don't even really mean a lot because we have minerals in our bodies and all that. But anyway, the term sticks. And organic chemistry specifically refers to, when we use that term now, we're going to talk about compounds or molecules made mostly from carbon and hydrogen. So that's going to be the main part. Think about the stuff we've looked at so far, things like sodium chloride or some of these other salts, potassium nitrate. Those would be the inorganic chemicals, things not based on carbon and hydrogen. And then they're not only made of carbon and hydrogen, they have all kinds of other elements in there, mostly non-metals is what we'll talk about. So things like oxygen, nitrogen, sulfur, the halogens, and other stuff. So there's certainly other things in there, but the molecules that we're going to focus on are made from carbon and hydrogen. That's going to be kind of the major focus of that. So let's review a little bit the chemistry of carbon and hydrogen, or how they connect to each other. We go back to those Lewis structures. How many valence electrons does a carbon atom have? Close. 4, right. So 1, 2, 3, 4. Which means how many electrons does it want to get a full octet? 4 more to get 8. So it's going to bind with, it's going to make 4 bonds in general. Now the simplest organic compound is carbon bound to 4 hydrogens. So we take our carbon, we take 4 hydrogens with their 1 electron, and we make a compound that looks like this. And the name for this is methane. Now we often write our compounds like this, and we didn't talk about that part of the earlier chapter about molecular shapes. But it's kind of important for organic compounds that this is not the shape of this compound. The way we have it written right here, what does this angle look like? You gotta remember your angles? Yeah. So it looks like a 90-degree angle here, but in the actual compound, it's not. Let me see if I can find a good picture of that before we try to draw it, so we know what we're talking about here. What page is this? So what it actually looks like, I'm going to pull this picture out, and then we will, and then we'll show how we draw it in 2 dimensions. It actually looks like this. Yeah. So you can see it's really not 90 degrees. It's got a 3-dimensional shape where 2 of the things are coming out at you and 2 of them are going back into the plane of the screen there. So it's not flat 90 degrees. And the reason for that is that this actual angle is larger than 90 degrees, which means that the electrons in the hydrogens can be farther apart from each other. Electrons have negative charges, and negative is a repulsion. Negative things repel other negative things. So those things want to be as far away from each other as possible. And that's why it adopts this kind of a shape instead of this. The way we write that, the notation we use for that, is called dash wedge notation. And it looks like this. So we put our carbon in the middle, hydrogen up here, and another hydrogen here. And we'd say, well, those two hydrogens are in the plane of the screen, are flat right up against that. And then if those two are flat, we're going to have one that comes out at us, and we draw a wedge to show that. And then we have one that goes back behind. And we draw a dash to show that one that goes back behind. So these two over here are actually right on top of each other if you're looking at them in a real structure. But since then we couldn't actually see it on the paper, we draw them slightly apart so that we can actually see it. But that means this one's going back and this one's coming out at us.
That's called
And that's called a tetrahedral geometry. A tetrahedron is a shape with 4 equal sides and equal angles. So it's like a pyramid, but not with a square bottom, with a triangular bottom. So everything's a triangle. That's called a tetrahedron. And so this is that shape if the carbon were right in the middle of that tetrahedron and the hydrogens were at all the points. Yeah. All right. So now we're going to build up and look at some larger molecules that are all based on this. The nice thing about the organic molecules is that the basic principles apply. There aren't a lot of crazy exceptions or having to count electrons on one thing versus the other. In all the compounds we see, carbon's going to have 4 bonds, hydrogen's going to have 1 bond. And we're just going to think about different ways to put that together. So let's always keep in mind while we're talking about this that in these structures, carbon's going to have 4 bonds. And hydrogen's going to have 1 bond. And we're never going to draw structures that violate those rules. All right. The first category of compounds we're going to look at are the simplest ones called alkanes. Alkanes are compounds that are just carbon and hydrogen with single bonds. So no double bonds, no triple bonds, no other kinds of atoms, just carbon and hydrogen. These types of compounds are not very reactive. These are the compounds that we get mostly from dead dinosaurs and things like that. We pull them out of the ground. We burn them for fossil fuels, but beyond burning them, we don't do a whole lot with them because they're not very reactive. Although, of course, they are really important by virtue of their being combustible. So we'll kind of make a list of going simple to more complex. The most simple alkane is the one we just drew, CH4. And we'll just draw the structure flat for now so we can see it. We're going to make a table here. This is called methane. The next one, if we have 2 carbons, how many hydrogens do we have to have? Close. Yeah. 6. So we got to have, because each carbon needs 4 bonds. So we need 6 hydrogens to fill up all those spots. So that's going to be C2H6. The name of that one is ethane. And these two, being the smallest, lightest alkanes, these are the major components of natural gas. So when we turn on our gas here, for our Bunsen burners, or to heat your house, hopefully your house is heated, it's cold out there. That's the gas that you're using to heat. These things together. Now, as you will probably get, well, you'll know for sure in a little bit, it gets kind of annoying to write these structures out as these things get bigger and bigger. When you start talking about having to put a hydrogen out on every single carbon and surround them, and you've got 4 or 5 or 6 or more carbons, it starts to get a little tedious to draw all that out. So we're going to look at a couple ways to condense these structures down, to make them a little bit smaller or a little bit easier to write while still conveying the same amount of information. And that's going to be called a condensed structure. So we'll write those over here. For methane, you can actually condense it all the way down and just say CH4. That tells you everything you need to know. We know carbon has 4 bonds. There's just 1 carbon, and there's 4 hydrogens. There's really only one way to make that molecule. As long as you know that that carbon has to have 4 bonds and hydrogen has to have 1 bond, just saying CH4 information to tell us exactly what to do.
So then ethane would just be C2H6.
It would, but there's actually a nicer way to condense the structure so that you don't make people do more work when they're trying to figure out what you're talking about. Let me show you what I mean. Condensed structure for ethane is going to look like this. CH3, CH3. Now we could say C2H6, but if you get if somebody says, hey, draw a structure for C2H6, well, then you got to lay it out, and you got to get the carbons there, and then you got to figure out where the hydrogens go. So there's an extra step there. If it's CH3, CH3, we know here's a carbon with 3 hydrogens, here's a carbon with 3 hydrogens next to it. That's it.
That's it, okay.
Yeah. And sometimes, especially for more complex structures, the lines are drawn in the condensed structure also. So we might go like this. That would be another type of a condensed structure. All right, so now I'm going to give you the next formula. It's C3H8, and it's called propane. That's propane gas like you get in the tank. Well, that's actually liquid propane that you run your grill with, or maybe your house if you live off the electrical grid. So I'm going to ask you to fill in the rest of that. See if, just based on the rules we've talked about, carbon's got 4 bonds, hydrogen's got 1. Can you draw a structure for propane with 3 carbons and 8 hydrogens? And then can you draw a condensed structure just like we did with methane? Give it a try. Mm-hmm.
Is there a way to condense CH8 apart from what you have there?
Let's think about it. Let's think about it. So what does the structure look like?
C.
Okay, C. So then you've got, okay, so 2 H's in the middle and 3, like that. Okay, great. So then what would our condensed structure look like? Yeah, we want to tell people a little bit more information. We want to say not just how many of these and how many of these are there, but how is it connected. So in this case, we might say CH3, CH2, CH3. To say, okay, here's 3 carbons. There's still 3 carbons in a row, but we're just going to condense the hydrogens onto the carbons. You can't, no. That will start to become confusing as we... Actually, you sort of can, but we'll get to that in some of the more complex structures. All right. So let's continue. C4H10 is called butane. Butane is just almost a liquid at room temperature and pressure. That's lighter fluid. So in your lighters is butane. Speaking of which, a reminder, in January, you can't smoke in Harper anymore, anywhere. Parking lots.
How did that come up from butane?
Because the lighters. Lighter fluid. Yeah. It's actually statewide. It's a state law. It's not just Harper. So
Can't smoke any, wait, you're not on smoke on the street.
you can't smoke on any
Thank
schools
God.
anywhere on the
That's
property.
awesome.
Is it weird that like I don't like smoking, but I like to smell cigarettes? Like it reminds me of my grandpa.
No, I'm kind of the same way.
Yeah. Like it literally reminds me of my grandpa.
Yeah. Well, mine doesn't remind me of my grandpa, but I feel the same way.
Yeah.
I don't smoke, but I like to smoke.
Like it just brings back memories.
Yeah. The Subway should start making like nicotine gum sandwiches or something for people who really need it when they can't get outside. All right, so you got it? Think so? Almost? Okay, give it a minute.
I'm happy they're passing the law. I scolded someone in the beginning of the semester because a grandma was waiting for their daughter to come out of class. And the student, her daughter had to have been like maybe 2 years old, if that. And these 2 Chinese people are literally 5 feet away from them smoking like hundreds of cigarettes, like the long ones that just linger. And it was the beginning of the semester, so all of the breeze was just flying right in this little girl's face.
Oh, that's just
And
awesome.
she's eating a sandwich. And I'm leaving this class and I just stop and I stare at the 2 Chinese people. And I had just I said, do you mind? You see this little girl is trying to enjoy her lunch with her grandma and you're ruining it. Walk 5 feet away so this little girl can enjoy her lunch. And they looked at me and they started like talking Chinese and probably should have talking, but I don't know.
Probably.
I don't care. I felt better afterwards.
All right, so butane, it's going to be 4 carbons in a row. Something like this, right? Is that what you got? Great. What's your condensed structure look like?
CH3 to
Oh, we will, don't worry.
to CH2 to CH3.
Yeah. And we could do the same thing. So now it's going to get a little bit trickier because more than 4, there are more possibilities for how you could draw these things. So the next one, actually, even with 4, there is. So before we go on to the next member of the family here, can anybody think about how you might, without looking it up, draw another structure, a different molecule that is still C4H10, still has four carbons and 10 hydrogens? Anybody think of a different way to do that? You can't, because hydrogen needs one bond, so they can't connect anything. Either way, but it's got to have the same number of carbons and hydrogens. What were you gonna say? Yeah.
You just have one carbon, four hydrogen, another carbon, and that little leads up.
Nope, they've all got to be connected, and they've got to follow all the same rules. All right, we'll come back to it. So let's look at the fifth one. So the fifth one, I'll leave you totally on your own. Come up with a formula, a structure. I won't leave you on your own for a name. And a condensed formula for the next member of the series, which is C5 pentane. So in this case, it's probably helpful to draw the structure first, so then you can count out how many hydrogens you need to get the whole thing done.
So this one is the 5 carbon.
Yes.
How many are you?
You have to figure it out. Yeah.
Is there like a scale or something that like you made it like any numbers like that?
You can't. Yes, there is a formula, but you can just put 5 carbons in a line, and then just add enough hydrogens so that all the carbons have 4 bonds.
So it's not different?
So what have you got so far? Let's see. Right. So then this is a different way you can do it.
Carbon has
And we'll talk about that. Because there are a couple. There's actually 3 different ways you can do it.
example.
I was trying to figure it out, but I didn't know. When you said that, I'm like, oh, yes.
Each one needs 4 bonds. So you make it like 4
Oh, that's now.
Yeah.
Yeah. Okay. All right, let's look at it. So some of you found some other alternatives here, which also work. What did you come up with for the formula? C5H12. So if you look back, before we do that, if you look back at these formulas, you'll notice there is actually a pattern. The number of hydrogens is always double the number of carbons plus 2.
Oh.
If you look at the chain, each carbon has 2 hydrogens, and then there's got to be 2 on the end also. So that's where the plus 2 comes from. So even if I said C20, how many have? 42. Because each carbon's got to have 2 hydrogens, and then there's 2 on the ends.
So you double carbon plus 2.
All right, so now we draw the structure. Now there are 3 different ways to draw this one, but I'll draw the most obvious one, which is just putting them all in a line. And now you can see it's really starting to get tedious to draw all the hydrogens in. All right. So now it becomes a lot easier to go CH3, CH2. Like that, right? All right. And I believe the you have to check on Blackboard, but I believe that you need to know the first 6 names. So let me get a, we'll put a chart on here so you can see them. So here's a nice table from your book. I'll just take part of it. And stick it in the notes here. So for the rest of them, one big part of this chapter is going to be how to name these things, what we call these things. And so I can't remember which ones it says exactly on Blackboard, but whichever ones it says, you need to know those. And then any beyond that, I would give you the names for. But here are the names for the different sizes. So we did the first 5, and then after pentane comes hexane, heptane, octane, nonane, and decane. You see that? I think you need to know the first 6. We can check that to make sure.
This is for the test or the final?
Any, both. All right, let's take a little break there, and we'll come back and talk about isomers and some of the names. So let's take 15 minutes. Go smoke all your cigarettes. Come back.
Should I ask for you're welcome?
Second one, we'll let you go quick.
You can collect yesterday.
No, because that's going to be due on Monday. Oh yeah, that's right. You're in the other section. It's quite a group.